Welcome to a lecture on CNN for dense image labeling or dense prediction, and then we would cover this briefly, and then we would move on to generative adversarial network. We don't need much of dense prediction for this course, but since we need some basic concepts on dense prediction, because they would be used in generative adversarial networks or GAN, so that's why we have to cover it quickly and briefly. So let's begin. Okay, so dense image labeling or dense prediction is basically when we predict the label of an image for each pixel. So for example, we have if we can see these images, previously we used bounding boxes and predicting labels for objects within those bounding boxes. That what we called object detection, or we could have image classification, which is the simplest version of using classification learning on images, where we just label the objects in the image without bounding them inside boxes. Another example is semantic segmentation, where we segment the image into different colors based on the type of the object. So for example, all the sheep's hair are of the same color, the person is of another color, and the dog is of another color. Then we have instance segmentation, where each instance is given a different color to identify them or to detect them. These two types of tags are also called panoptic segmentation. So for semantic or instance segmentation, we need dense prediction. That is, we need to predict the label for an image based on each pixel, so that we can then segment them based on their labels. The lecture outline is we would discuss some early hacks that were used for dense prediction. These include hypercolumns, zoom out features, then fully convolutional networks. Then some deep network operations for dense prediction, which includes transposed convolutions or deconvolutions, unpooling, and dilated convolutions. We won't go into details of instance segmentation or other dense prediction problems for the sake of this course, but you are welcome to read the full slides if you are interested in it, which I would share later. So let's see what early hacks people used for dense prediction. So dense prediction earlier was used as a post process on top of an image classification. So just like in the previous lectures, we used image classification and object detection on images based on CNN. So if we use a post process after the object detection or after the classification for pixel wise predictions on images, that would be we would be using an early hacks that was implementing the dense prediction as a post process. So as expected, it increases the computational complexity, since we would be applying dense prediction on top of an already developed giant network which was used for the classification. So here is an example architecture. We have an input image, we have some convolutional layers, like there are 96 filters here, 256, 384, and so on. And then finally, when we get to this last convolution layer, the output is then converted in using upsampling or some other technique, converted into the resolution of the full image, and then the class or the label is detected for each pixel of that final feature map. Another idea or another way to do dense prediction is called hypercolumns. The idea is to obtain a feature representation for an individual pixel, then upsample all feature maps to original image resolution and concatenate values from feature maps above that pixel. So that is, we have an input image. We take the input image, get it through some convolutional layers, and since at the end of each convolution layer you get a feature map, So each feature map is upsampled to the image resolution. Since the output of a convolution layer is of lower dimensionality than the input, because of the convolutions, because of if the convolution is done without padding, so we need to upsample it. That is, we can upsample, for example, if a pixel is needed to be converted into 4 pixels, then you can give all those 4 pixels the same values as the original pixel. So we can do upsampling by this simple technique, and such that each feature map is converted to another feature map which is of the same resolution as the input image. Once you do these upsampling on different levels of this convolutional neural network or different feature maps, now all these feature maps after upsampling are of the same dimensions. Then we concatenate them. You can see at the figure here, such that for corresponding to each pixel, there is a value in the feature map, in all feature maps. There are multiple outputs, multiple feature maps at the output of each convolution layers, and there are multiple convolution layers. So if we concatenate all these values corresponding to the pixel in a column or in a vector, we call it a hypercolumn. Then we can use these hypercolumns to train a neural network, for example, a multi-layer perceptron. For example, we are doing that. We are concatenating them, then applying a sigmoid layer, and then following by a classifier, so that for each pixel, and that input is a pixel, and for each pixel there is an output, which would be the label, which is the label of the corresponding bounding box, or the label of the object which is in that region. Another way to, which is a bit similar to the hypercolumns, there is zoom out features. So in zoom out features, we first convert the pixels into super pixels. That is, instead of using one pixel at a time, we combine multiple pixels. For example, in a window, we call it a super pixel. Then that image or that input is passed through different convolutional layers as before. Each convolutional layers is producing a feature map or as an output. We can also, and then we use average pooling over the superpixel to get the per pixel value of the feature map. For example, in the first convolution layer here we have 64 filters, so the so it would be a 64 dimensional vector, which is the value from the feature map corresponding to the input pixel for each filter or at each feature map. Similarly, at other layers, for example, at this layer we have 128 filters, so the output is a vector of 128 dimensions. Another convolution layer where the output is of 256 dimensions. So we can have many layers, several layers, then concatenate all these outputs, so we get a matrix. So that is phi 1 is the first column, 64 dimensional column, then phi 6 the sixth column, and so on. So once we concatenate them, then we can use these as inputs to further a new or another neural network, which could be a convolutional neural network or a fully connected network. So that is, we can use we can do the per pixel prediction or the dense prediction using zoom out features. Let's see some example results. Here we have an image, and here is the output. The areas or the pixels corresponding to a specific label or specific region corresponding to an object are segmented, so, and are given a different color. Here is another example, some more examples, and so on. And these are all examples of segmentations based on objects. Okay, so when we have an architecture or a method to perform a certain task, we also need an evaluation criteria, so as to evaluate how our model is working. So for that we usually use a metric which is called mean IOU, that is intersection over union of predicted and ground truth pixels for each class, and then averaged over all classes. So that for each class you'd calculate the union of predicted and ground truth pixels, or the pixels inside those regions, and divide them, calculate the intersection of those two regions and divide them on their union. For a good performance, this value should be as high as possible. So for ideally it should be equal to 1. When the intersection is equal to the union, that means that the two regions are completely overlapping each other. So let's compare different methods. The zoom out features is evaluated as at 69.9 for the WOC 2010 dataset, 69.4 for 2011, and 69.6 for 2012. As compared to hypercolumns, it performs much better, significantly better. There are other methods, some of them we'll discuss shortly, and for example FCN8S, which performs poorly as compared to hypercolumns or zoom out features. Okay, so the next method is fully convolutional network, which we have seen used as a comparison to zoom out features here. In a fully convolutional network, as the name suggests, all layers are convolutional layers. So from the input till the output, there are only convolutional layers and no fully connected layers. So we need to design a network with only convolution layers and make predictions for all pixels at once. So here is an example. We have a feature map generated by 96 filters of convolutional layer, then 256 filters, 384, and so on. We keep increasing the number of filters and also increasing the size of the filters till we reach at this point where we have 1000 filters, and finally this is upsampled and interpolated to create this heat map where the pixel values, the intensity of the pixel values are mapped to a color and its intensity, and it shows a segmentation of the input image. Let's see how fully convolution network works. And also the question is, can the network operate at full image resolution? What if we design a fully convolutional network where each feature map is of the same resolution as the input image? So for example, we have an input image of 3 by h by w dimensions. 3 is the number of channels for 3 colors, h is the height of the image, w is the width of the image. The convolution number of the convolution layers are such that the first convolution layer is such that, for example, you can use padding, that the feature map is of the same dimensions as the input image, except for the depth. We can increase the number of layers or decrease the number of units or the number of filters to control the depth. So all the feature maps produced by these convolution layers are of the same dimensions, h by w, as the input image. And finally, our final convolution layer produces an output which is of dimension c by h by w, where c is the number of classes. That means that we would need, in the final convolution layer, we would need the number of filters should be equal to the number of classes, and the size of the filter should be such that the each feature map is of h by w resolution. Once we have this output of the final convolution layer, then and since this dimension or this resolution is the same as the input resolution, so we have c values for each pixel corresponding to each pixel. Then we can use an argmax to predict the label of each pixel. That is because each pixel is represented by c different values corresponding to c different classes. So whichever is the highest value, we would assign that pixel that certain class. So for example, if class number 6 has the highest value, or the output of the sixth filter is the highest, then we assign the class number 6. So this is our predicted image, or segmentation, or per pixel prediction, and represented by different colors. But the problem with operating the network at full resolution is that it increases the computational complexity, as the size of it's not doing any dimensionality reduction. Also, if you are not using padding, then the output feature map would not be of the same dimension as the feature input features or inputs. So a practical solution is, and we need such solutions because we want the output here at the end to be of the same resolution as the input image. So we can solve it by using first downsampling and then upsampling. That is, we can reduce the resolution through applying convolutional layers, and probably also downsampling to a smaller resolution like this box, and then passing through some more convolution layers or upsampling to produce a feature map of the same resolution as the original image, and then use it for the final prediction using argmax. So let's see how it works using fully convolutional networks using different upsampling and downsampling. So here's an example. We have and these are and the terminologies that or the naming conventions. Let's for example, if this is an image and this is the image after the pooling, passing through the first convolution layer and then pooling, so it's now downsampled, and then again downsampled, then again downsampled, again downsampled, again downsampled, so that at the end the resolution is reduced by 32. Now we can then use either use upsampling or on this output to produce a 32 times upsampled prediction, which is called FCN32S, or we can use 2 times upsampled prediction, so that for each pixel is now represented by 4 pixels, and this feature map is of the same dimensions as the output of this pool 4. Then we can combine these two to produce, and then upsample to produce the 16 times upsampled predictions. Or we can get this downsample feature map and take the upsampling of 2 times from these two feature maps and combine them to produce an 8x upsampled predictions, which is called FCN8S. So as you may expect, this would be this last one would be a better representation of the content or the information in the image instead of this 32x one. Let's compare them on the Pascal 2011 validation data. If we use the FCN32S fixed architecture, then we have a pixel accuracy of 83%, mean accuracy of 59.7, and mean IU of 45.4. If we use FCN32S, then the mean IU is a bit improved. 16S give further improvement on the as compared to 32S, and 8S gives us the best result, but at the expense of computational complexity, since there are more operations involved in using FCN8S. Here you can also see the results in these in the form of these images or the segmentation. This is the ground truth. FCN8S is more closer to the ground truth as compared to FCN16S or FCN32S. Okay, so this was about these 3 hacks of pixel-wise predictions or dense predictions, that is hypercolumn, zoom-out features, and fully convolutional networks. Let's look at some deep network operations for this dense prediction, which includes transposed convolution and unpooling. We won't go into details of dilated convolutions for the matter of this lecture. Transposed convolution. Okay, so regular convolution is that if we have an input, let's say a 4 by 4, there are 4 pixels at the width and 4 pixels at the height. There are 4 columns and 4 rows, and if it's convolved with the 3 by 3 filter, we get a 2 by 2 output. So you can think of it as a feature map for this corresponding input. In matrix vector form, we can write this the filter coefficients in a fat matrix, where the entries where there are no multiplications involved are represented by zeros, and the remaining entries are represented by the coefficients of the filters, and they are multiplied with the input, which is flattened to make into a vector, and the output is this vector, which can be converted back into this matrix form, that is Z11, Z12, Z21, Z22. And you can see from this multiplication that what Z1 would, so Z11 would be equal to W11 X11, W12 X12, then W21 X14, and so on. So you would get Z11, Z12, Z21, and Z22. So this is a regular convolution where the input is 4 by 4 and the output is 2 by 2. Let's transpose this filter matrix now. So at the output we have which was considered as the input before, that is a 4 by 4 matrix, and at the input we have a filter, convolution filter, but which is transposed, and then it's convolved with the with the output, which was actually the output, but now considering it as an input of smaller dimensions. And we can look at this in the matrix vector form as this matrix vector equation. So it's because of the transpose, now it's a long matrix, and then it's multiplied with the outputs, which is now the input, and producing the outputs, which is now which were actually the inputs. So this process is called transposed convolution. So as you can see, that a regular convolution produces a result which is of less dimensions than the input, but a transposed convolution produces a result which is of larger dimensions than the input. So if you consider this as the input and this as the filter, so and even the filter is of larger dimensions than the input, and this is the output. Transposed convolution is not exactly the inverse of original convolution, but there's inverse in terms of dimensionality. So with transposed convolution, with let's say if there is a 2 by 2 input and 3 by 3 filter, the output would be 4 by 4, which is exactly in terms of dimensionality, which is exactly opposite of the convolution. So if we use transposed convolution, we can achieve the effect of upsampling or converting the image to the image resolution, and still using all the information in the image, or taking more information from the image. This is also sometimes called deconvolution, but it's a misnomer which is misleading sometimes, because it's not the inverse of a convolution. So let's see how transposed convolution works. We can go one by one to produce these different outputs, and what are they equal to. This 1D example of the transposed convolution, you can look at these animations to understand how these works. Okay, so we can use transposed convolution for upsampling by backward strided convolution. To increase the resolution, we have to use the output stride more than one. For example, for stride 2, we can dilate the input by inserting rows and columns of zeros between adjacent entries. and convolve with the flip filter, sometimes called convolution with fractional input stride 1 by 2. Okay, so we can also use do upsampling by unpooling, which is an alternative method for upsampling to transpose convolution. For example, we can use max unpooling. So if you remember pooling, in pooling, when we combine the output of we combine 4 pixels, we take the maximum of it as our new value for the pixel, and it's downsampled. So each 4 pixels are downsampled to 1. The unpooling would be a process where one sample, 1 pixel is converted into a higher number of pixels, for example 4 pixels, where one of the value is the same as the input and all the other values are equal to zeros, because when you are given this input you don't know what other values are, so we can replace them by zeros. In this case, if we use max unpooling, the output is sparse because there are more zeros than non-zeros numbers, so it's typically followed by a transposed convolutional layer, because it is now a favorable, it can be used as a favorable input because there are less number of parameters to train, and so it could be used as a good pre-processing step for the transposed convolutional layer. Okay, this is an overall architecture where we use a fully convolutional neural network with upsampling and downsampling through max pooling or max unpooling and convolutional and deconvolution. Overall, this kind of architecture is called deconvnet or deconvolutional network. So in this example architecture, you can see there are multiple types of layers, like there is convolutional layers, and then there are max pooling layers, till we reach to the lowest dimensions. So after that we used we start deconvoluting it through unpooling and using transposed convolution till we reach to the image resolution. Here are some results on the deconvnet. There is the original image. If you use a 14 by 14 deconv network where there are 14 steps towards the downsampling, or 14 layers and 14 layers for the upsampling. Then 28 by 28 using unpooling, 28 by 28 decon, 54 by 54 unpooling, and so on. As you can see here, if you increase the number of layers, we get a better segmentation, a better output. For example, in this last one, which is very close to the original image, and the output is also very dense. But if we use unpooling, then the outputs although becomes better, but it's always very sparse. The sparsity or these dots are because of the zeros in the unpooling output, because there would always be more zeros than non-zero numbers in the output feature maps, so you'd see these blind spots if we use unpooling unpooling layers for the upsampling. Here are some comparison of the results on deconvnet with the previous methods. The MIOU, the mean intersection over union for hypercolumns, or 59.2, but with deconvnet now it's significantly increased to 69.6. But if we take the ensemble of fully convolutional networks and deconvnet, we get a much better performance, which is 71.7. Alone, the fully convolutional networks ATES that we used before produce not a very good result, but still better than the hypercolumns, but worse than the zoom out. So this is what is considered enough for the dense prediction. Next, we move on to another topic, which is generative adversarial networks. That is the main topic of today's lecture. So let's end this part here and keep tuned for the next part. Thank you very much.